Alright, hello class. Today we're going to be talking about section 4.2, which is on local extrema and concavity. So last time we talked about absolute extrema, like absolute maxes and mins. But this time we're going to look at trying to find local maxes and mins and how we do that. If you aren't given a graph, or say you're just given the formula and you find the critical points and you sort of have this idea of where a local max and min might live, how would you analyze them? Well, it's actually very simple. You see it at a local max. This is of course a point where the tangent line has a horizontal, or it's horizontal, so right, the slope is 0. That of course gives us the critical point. But specifically, a local max happens when f goes from increasing to decreasing. Right? So in other words, it's a specific type of turning point. We usually call these turning points where the graph changes from increasing to decreasing. Or, as we see with this local min, it's changing at this point from decreasing to increasing. Okay, and that point of change happens where we have that horizontal tangent line. So this is essentially how we're going to check to see whether each critical point we have corresponds with a local max or a local min. Right? So to analyze a critical point, you just check to see if it's increasing or decreasing on either side. Okay? Now, up until this point, determining if a function is increasing or decreasing on a certain interval was actually a really tough thing to do. It was kind of complicated. But now that we have the derivative, okay, which tells us the rate of change, right? The derivative gives the rate of change of f. Now, once we have the derivative, it's actually very simple to see if a function is increasing or decreasing. If f prime of x is positive, okay, what does that tell you about the function itself? Right? If you get a positive derivative, that tells you that f, the original function f of x, is increasing. Right? And if you find that the derivative is negative, right, that gives you that f of x is decreasing. On that interval, wherever the derivative is negative. Right, so that's a very simple way to tell if a function is increasing or decreasing now. Before, that was a super hard thing to do without a graph, to prove that something was increasing or decreasing. But now that we have the derivative, it's as simple as just seeing whether it's positive or negative, which is actually a very easy thing to do. And the other case, if f of x is equal to 0, okay, or does not exist, actually let me not put that. If f prime of x is equal to 0, then it's possible that f of x has a local extrema. local extreme there. We have to add the d and e as well to get that to be a two-sided thing. So if f of x has a smooth turning point, right, a smooth local extreme, so this is true, and I should actually still be careful because this is still just one-sided, since we could have a critical point there that does not actually mean we have a local extreme. So careful about that. All right, we'll see that in a couple of examples here. But so basically what we're going to do is we're going to find our critical points, and to the left and right of each critical point, we're just going to see whether the derivative is positive or negative, and that's going to tell us, whether we have local maxes or mins. So to analyze critical points, we just check the derivative. On either side. Right. It's that simple. Okay, this brings us to what is called the first derivative test. I think it's called that for two reasons. One, I mean, it's the first test that you learn. And two, it's a test that uses the first derivative to do so. So here's how it works. If we have a critical point, so if C is a critical point of f of x, okay? And again, this is a way to check or analyze critical points. And if f prime of x, if it changes from positive to negative, okay, and I should say at C here, then f of x has a local, it's going to have a local max at C. And think about why. If f prime is changing from positive to negative, right, so going from positive to negative, that means that f goes from increasing to decreasing, right? Or it goes from rising to falling. Therefore, it must have a max there, right? So it's got a local max in this case. Okay. Then, if f prime instead changes from negative to positive, so if it's doing the other way, what must f have here? Of course, a min. It's going to be the opposite. And if you think about why, if f prime, so if f prime changes from negative to positive, that means f is changing from decreasing to increasing. So that means it's falling, then rising. So of course we must have a min there. Okay. Now let's say that f prime does not change at all, right? It goes from, say, positive to positive or negative to negative. Then f of x, we say, has neither a local max nor local min, right? That's possible. We saw an example of that last time, I believe, and we'll look at another example that deals with that here. But basically that ends up being your leveling off points. And if you think about it, if f prime goes from positive to positive at C, that means f is going from increasing to increasing, right? And what that looks like, if you're going from increasing to increasing, that basically just looks like you're going rising to rising. Of course, that is definitely not a local max or a local min. Right? It's pretty clear. All right, so that's the first derivative test. Let's look at a really quick example to kind of show why or how it works. Something where we already know the answer. We're going to go back to our tried and true x squared example, because we know what x squared looks like, right? X squared makes a u, right? So here at 0, we already know that it has a local min. And it's essentially a global min, right? But so we're going to use the first derivative test to show that this is a local min, right? And we're doing this just to kind of introduce us to this idea. Obviously, with x squared, we already know it's there. But we're going to use this same process on functions that are a lot more difficult. Okay, so let's do f prime of x. Right, there's 2x, and to find the critical point, we set it equal to 0, and we get that x is equal to 0, so there's my critical point. Okay, and to use the first derivative test, so using the first derivative test, right, what I like to do is I usually just set up a number line, plot my critical point on it, and then from the left and right, look at f prime, because what I've essentially done is I've now split up the interval. My only critical point is 0. That means that's the only place where f is allowed to turn around, right? It's the only place where f is allowed to change from increasing to decreasing or vice versa, right? It's the only critical point. Therefore, all I have to do to check whether f prime is positive or negative in this entire interval here and this entire interval here, right, negative infinity to 0, 0 to infinity, is check a single point. Okay, so f prime, if I check, I don't know, -1, it doesn't really matter, but if I plug in -1 into f prime, I get -2. So it's negative on this side. Okay. That means f is decreasing or going down. And to the right of 0, if I plug in a positive number into 2x, right? And maybe I should show what I'm doing here. F prime, here I might plug in -1, which would give me -2. And here, on this side, I'll plug in +1, which will give me +2, which is positive, which tells me that our original function f is increasing. Therefore, it's pretty clear to see right here at 0 that this is a local min. Okay? Right, which we already knew. I mean, we know that x squared goes from decreasing to increasing, but, you know, we're going to start looking at functions where we don't already know that. All right? Now, that's basically how the first derivative test works. We're just, you know, checking either side of each critical point, and we're plugging values into the derivative to see whether they're positive or negative. And now, the big thing about this is I know that this guy is negative on this entire interval from -infinity to 0, because let's say over here there's a spot where it became positive, right? Say it's negative, but there's a spot where it becomes positive. What would have to happen in between? Think about that. We would have to find a place where f prime is 0, but we only found one spot where f prime is 0, right? So what we've basically done is split up the interval into the only possible places where f prime can be 0. In other words, the only possible places where f could possibly have a turning point or possibly have a local maximum min. And we've basically split our entire interval, -infinity to infinity, into a more manageable 2 chunks and just checked both of those regions. And then we only have to check a single value, right, since we found the only places where it can change. All right, let's look at a more complicated example. Okay, so here, for our next example, we're going to try and find and analyze the critical points okay, of this following function here. F of x equals 1/4 x to the 4th minus 2/3 x to the 3rd plus 100. And what it means by find and analyze is tell me whether they are local maxes, local mins, or neither. Okay, so what's the first thing we do here? And if you said take the derivative, you're right. The first step of pretty much every problem that we'll be doing here will be take the derivative. Now, I'm going to go ahead and go through this. 1/4 x to the 4th will be x cubed, and 2/3 x cubed, that will give us 2x squared, right? Because the 3's cancel, the 4's cancel, and the derivative of 100 is 0. And to find the critical points, what do? Set it equal to 0 and solve. So my advice always, as you probably started to see in your last worksheet, is always factor if you can. So we're going to go ahead and factor x squared out, and then we get x minus 2. So we get x squared times x minus 2. Now I'm going ahead and calling this f prime as well, and you'll see why in just a second, because this factored version is going to be a lot easier to deal with. Alright, so if x squared times x minus 2 is equal to 0, that means x is equal to 0, or x is equal to 2. Okay, so these are my critical points. Alright, now we get to the analysis. Now here's a part where a lot of people will mess up. You have to, if you're going to use a number line, you have to put both critical points, actually all critical points, no matter how many you have, on the same number line. You cannot check them separately. You have to check them together. Okay, so that means I have to check some values in from the left of 0, in between 0 and 2, and to the right of 2. Right, so we're going to check f prime, and it's going to tell us things about f. Alright, so f prime, well, to the left of 0, I'm going to pick something like, doesn't really matter, but -1 is probably a good option. Now, here's the thing about this factored version. Now that we have this factored version, I'm going to plug it into here. And the cool thing about having it like this is this x squared is always positive, right? Right, x squared, so no matter what I plug into x squared, this thing is going to be greater than or equal to 0. So it's really this that tells me whether f prime is going to be positive or negative. So if I put in -1, right, if I choose a -1, I don't like to put it on my number line because it kind of it's kind of tough to tell which is your critical points and which aren't at that point, but let me go ahead and split this up. If I plug in a -1, -1 minus 2 is going to be negative, so I have a positive times a negative. So say f prime of -1 is positive, and that's all I care about. I don't care what the number is. All I need to know is whether it's positive or negative. So you can actually stop the second you know that it's positive or negative. So f prime is positive here. That means f is increasing from -infinity to 0. Okay. Now, between 0 and 2, let's say I put in something like 1. Let's look at f prime of 1. Well, this, again, is always positive, but if I put in 1, I get 1 minus 2, which is negative, so instead of saying equal, let's just say, okay, that's negative. All right, which means that, sorry, I completely messed this up back here. All right, when you plug in -1, you get -1 minus 2, which is negative. My bad. Okay, so it's decreasing here. Very sorry. Very sorry. But the point of this is that at 0, this is a place where f goes from decreasing to decreasing. So I can already say that this is neither. Okay. Then from 2 onward, so to the right of 2, if I put in something like, we could do f prime of 3. This is always positive. 3 minus 2, that'll be 1. So this thing is greater than 0. So f prime is positive to the right of 2, meaning that f is increasing to the right of 2. So it's going up. So here at 2, the function's going from decreasing to increasing. So this is a min. Okay. So another thing that your problems will ask you will say, give the open intervals okay, on which f of x is increasing and decreasing. Okay, now it's very, very simple. We already have, when you do it this way with like a number line, the way I like to do it, you already have it, right? I have my interval split up into 3 subintervals. I have 2 to infinity, I have 0 to 2, and I have negative infinity to 0. Okay, so that means I could say that f of x is increasing on 2 to infinity, right? That's where f is increasing. And f of x is decreasing on, now here it gets a little funky, but basically we have negative infinity to 0, right? And union 0 to 2. Now you might say, well, why don't we say it's decreasing from negative infinity all the way up to 2? And it's because, is the function decreasing at 0? So is f of x decreasing at 0? Think about that. Because if you think about what's happening at 2, you would say definitely not, right? We have a local min, and at that point, it's the point where it turns around. But here at 0, it goes from decreasing to decreasing, which makes it look something like this. And the answer is actually no. If you're talking about the rate of change, that's where the function stops. The answer is no. At 0, f has stopped moving, or stopped decreasing for a second, right? So for, I'll say an instant. Okay, you can think of this as like a, you come to a stop at a light, right? Or you stop really quickly for something and then you continue on your way. Okay, that's what is happening at these leveling off points. There's still places where the derivative is 0. It's still where you're neither increasing or decreasing. So when you have situations like this, well, you've got to make sure that you split them up with u's or unions, that means. Okay. All right. Let's move on. All right, so that is the first derivative test. Next I want to talk about concavity, and we've already kind of dealt with this before, but basically, all right, the concavity of a graph, basically f is concave up if f prime of x is increasing. Okay, so if the derivative increases, all right, think about that as acceleration, right? If the derivative increases, so if your velocity increases, you're accelerating, right? That's basically what we're talking about. So concave up, you can think of meaning accelerating, okay? And f of x is concave down if f prime, or the derivative, is decreasing. So we can think of that as a function decelerating, right? So we've already sort of dealt with this, right? So I like to think of this as something we've already seen. This is essentially acceleration, right? But it's a general, it's an acceleration generalization. We're generalizing what acceleration is to really any function that we want. Okay, and basically, what we have here, let's say I have this graph, and if we want to maybe see where a function is concave up or concave down, well, basically what we're going to do, the tough way to do it is to look at the tangent lines. So with this graph, if I look at the tangent lines of this graph as x increases, okay, and I see that the slope starts really positive, really steep, right? So this might be a slope of like 10, and this might be a slope of, I don't know, 5, and this might be 1/2, and this is definitely 0. This is where we have a local max, okay? And then it starts to get negative, right? So maybe this is -1/2, and this is negative -2, right? And it starts getting steeper. So what are the slopes doing over time? Okay, so that's the question. And they are decreasing, right? They start at something like 10 and they decrease down to 0 and keep decreasing down to like negative whatever. So in this interval here, f prime of x is decreasing. Okay. Which means that from our definition, means that f is concave down. So f is concave down. Okay. So let's look at this other side. See if I have another color laying around here. Yep. So if I look at the tangent lines on this side of this point, right? Okay, so they start negative. So this might be, I don't know, -2. This might, and then they start getting shallower, so this might be -1/2 until right here, which is the local min, and it becomes 0. This looks like m equals 2 up to m equals 5, let's say. So what are the slopes doing here? They are increasing. So f prime is increasing, meaning that f is concave up. Now this point here, okay, in between, this is where the function changes from concave up to concave down. We call that an inflection point. Okay, that's a point where f changes from concave up to concave down. Okay. And that is often what is happening at these leveling off points. Okay. For example, here's a classic function with a leveling off point, right? X cubed. That's usually the first one you think about. I made it very extreme here for the record. But say on the left here, we almost have pure full vertical line, but it's not. I'm just exaggerating. But here's the tangent lines on this side. And then let's look at the tangent lines on this side. Okay. Now, here at 0, we have a horizontal tangent line. Okay. So let me put that in with green. Kind of hard to see, but there at 0 we have a horizontal tangent line. Okay. But to the left, what is happening to the slopes over time? They start very steep and positive, but start to level off. They never get to be negative because this thing's increasing over time, but they level off. Say this is something like a slope of 10, whereas this is something more like a slope of 1. Right? The slopes are decreasing, so f prime is decreasing here. So that means f is concave down. And on this side, we see that they're increasing. They start here at 0 and they start increasing up to something super steep like 10. So here f prime is increasing. Right, the slope of the tangent lines are increasing. That means f is concave up on this interval. So here, this was a leveling off point, right? That we didn't know what to call it before. And so often, when you have neither, right, a local max or a local min, what you have instead is an inflection point. Now, when you're talking about graphs, it often takes way too long to, do this with all the tangent lines. A quicker way to do it, okay, is when a function is concave down, notice that the tangent lines rest on top. Let me write that in purple so we know. So tangent lines rest on top, right? So they tend to rest on top when you're concave down, and tangent lines rest below when you're concave up, right? You see all the tangent lines kind of rest below. And the point where the tangent line looks to be flush with the graph, say you draw a tangent line and it matches the graph. So tangent line matches the graph at inflection points. Okay, so that's a bit quicker than trying to see if draw a bunch of tangent lines and see what's going on. You could just say, hey, they rest on the top of the function, therefore we must be concave down, and here they're resting below the function, therefore it must be concave up. And here, this is where, and this is really the most important part about it, is you can find inflection points on a graph very quickly by seeing where the tangent lines are flush or where they match the graph. Okay, and an even quicker way to do this, right? So we still need this idea to help us find inflection points, but graphically anyway. But does everyone see here when you're concave down, or specifically actually a concave up makes a U, or I like to say is a smile, but you can think of concave up, CU, it makes a U. And then concave down is a frown. So that's one thing to keep in mind here. Here, concave down, you see the graph is frowning on this side of 0, and it's smiling on this side of 0. Right, so concave up is a smile, also known as a U, and concave down is a frown. Okay, and it could be a half smile, half frown. Right? It doesn't have to be the entire thing. Right, so real quick, if we look at an example, I mean, we can pretty much immediately determine where it's going to be concave up and concave down. It looks like my inflection points would be here because a tangent line would look about flush with the graph there and about there. And notice inflection points matching the graph. This happens where the graph looks linear, right? Wherever it looks linear for a spot, that's usually where you have an inflection point. Okay? So what's my concavity here? Okay, this is a frown, right? So this is definitely concave down. What about in between here? That's a smile, so this is definitely concave up. And here, a frown, so this is concave down. Okay, so that's all well and good, you know, if you have a graph, but what do you do if, say, you have just a function? Okay, so remember, if we're talking about f prime of x increasing, and I said we can think about this as velocity, we can actually use the second derivative, because if a function is increasing, that means its derivative is positive, so that means the second derivative will be positive, which gives us that f of x is concave up. Right, and so if f of x is concave down, that means f prime of x is decreasing by definition, which means that f double prime of x is negative. Okay. And finally, in a much similar way, if f double prime of x is 0, we don't have a nice word for this like critical point, but this basically means that, let me say C. Okay, it's the same idea, but that means that f of x has a possible inflection point at C. It's still possible that it doesn't. Same thing with if you have a right, if you have the derivative is 0, that means you might have a local max or min, but you might not. The same case here. Alright. Alright, so I know that was a pretty brief look at concavity, and we're going to do a bunch of examples. I want to just get some things out of the way first. The last thing I want to bring up, and then it will just be examples from this point on, so just bear with me, is that, does everyone see that here I have a local max, and the function is concave down, right? And here I have a local min, and the function is concave up, and here I have a local max, and the function is concave down. And if I go back to this, concave down gives me max, concave up gives me min. And basically, if you ever have smooth turning points, that is always going to be true. So we can actually use concavity to help give us analysis for critical points. And that is what we call the second derivative test. So let me go ahead and give that very quickly. Okay, so here's what the second derivative test says. It's basically what we just talked about. that if a function is concave up at a critical point, then we'll have a local min, and if it's concave down, we'll have a local max. So basically, here's how it works. If we have that f prime of c is equal to 0, so a critical point, but only the type where f prime of c is 0, not an undefined. This won't work for the undefined case. Okay. Now, if f double prime of c is positive, then f of x has a local min at x equals c. All right, so it's a little opposite of what you might think. If the second derivative is positive there, we have a local min. But if the second derivative is negative there, we have a local max. Okay, and if f double prime is equal to 0 there, then unfortunately the test doesn't tell us anything. So this is basically just seeing whether the function is concave up or down there, and that tells you whether you have a local max or local min. And this uses this same idea that, say, concave down gives max, concave up gives min. Okay. And that's what we're doing. Now, there are some benefits to using the second derivative test. For some reason, students here tend to not like the second derivative test, but honestly, it's actually a lot quicker because you just plug the critical point straight into the second derivative. You don't have to find values and check the derivative from either side. But there are some problems. The second derivative test won't always work. For example, if it spits out a 0, then you have to use the first derivative test. Okay. So I'll just call that the 1dt. Right? So that's one good thing about the first derivative test, is that it will always work. But with second derivatives, the more you take derivatives for a lot of problems, right, the simpler the function becomes a lot of times. Not always, but a lot of times. Okay. All right. So let's go ahead and look at some examples. We'll use second derivative tests. We use first derivative tests. We will check for concavity, do all that stuff. Okay. So one thing I want to really drive home is that f prime, this gives increasing and decreasing. F double prime, this gives concave up, concave down. It's easy to mix these things up, okay? But be very careful about what each one of these does. All right, you need to be careful about labeling these things too, because it's very easy to get confused in what you're doing. Okay, so let's look at some examples. All right, so here's the example we're going to look at. F of x is equal to 2/3 x cubed plus 2x squared plus 1. All right, and then we're going to do everything. We're going to find the critical points. We're going to analyze them as local maxes, local mins. We're going to find the intervals that f is increasing or decreasing on. We're going to find the inflection points. We're going to do the whole thing. All right, everything we possibly can with this. All right, so first, we're going to find the derivative. Right? That's always your first step. In fact, pretty much on all these problems in chapter 4, if you don't take a derivative, you've done something completely wrong. All right. So f prime of x, take the derivative, that will be 2x squared plus 4x. And while I'm at it, I'm going to go ahead and take the second derivative, since we're going to be using that as well. So that will be 4x plus 4. No big deal. Now, we're going to find the critical points. And this, what we do is, this is when we set, of course, f prime of x equal to 0. Or see where it's undefined. But in this case, it's a nice polynomial, actually a nice quadratic, so it's not ever going to be undefined. So all we've really got to do is set 2x squared plus 4x equal to 0 and solve. And this is one where we can factor, so I'm going to factor out that 2x times x plus 2. And from here, it's very clear to see that x is equal to 0 or negative 2. So here's my critical points. All right. Now from here, I am going to analyze these using, basically I'll use the first derivative test on this side and the second derivative test on this side, just to show how both work. And a lot of these problems where you're having to do a lot of stuff, the first derivative test helps give you your intervals if that's what it's asking for. But otherwise, if it's not, the second derivative test tends to be a lot faster, and we'll see why in just a second. So here's the first derivative test over here. That's where we use our number line here. So I have -2, I have 0. And I'm going to start checking f prime here and seeing what I get. Okay, so we basically split our interval into 3 pieces. Okay, so over here, f prime of x, well, say to the left of -2, if I put in something like, it doesn't really matter, but you could do like -3 or -10 or -100. It doesn't matter because I've found the only places where f is allowed to turn around here. So if I put in -3, this is negative, and then -3 plus 2, that will also be negative. So I have a negative and a negative. So this ends up being a positive. Right? Which means that f is increasing, okay, from -infinity to -2. Okay, then between -2 and 0, and this you have to check in between. A lot of people will split it up and do it separately. I don't know why. You always set up a single number line, but I'm going to check, say, f prime at let's say -1. So if I plug in -1 here, I get a negative at -2, and here I get a positive because that's going to end up being 1. So this whole thing ends up being negative. So we have a negative right in between here. So that means f is decreasing from -2 to 0. And finally, from 0 on, if I put in any positive number, so you could do, say, f prime of 1, you're plugging in 1 here. So you get 2, 2, positive, positive, the whole thing ends up being positive. And again, I don't care what the numbers are, I just need to know whether it's positive or negative. And therefore, we have right off, just from the first derivative test, that we have a max here, okay, at -2, and a min here at 0. Okay. So that's the first derivative test. And the nice thing here is we also have the intervals that we need, right? F is increasing from -infinity to -2, it's decreasing from -2 to 0, and then increasing again from 0 to infinity. So for ask for those intervals, we have them. Now if I want to use the second derivative test, what the second derivative test says is basically, and I'll bring it back up here, basically you just take your critical points and plug them into the second derivative. Okay, so you're just going to plug CP's into f double prime and see what you get. Alright, so f double prime is up here, it's 4x plus 4. Okay. So basically you plug, alright, so plugging 0 into f double prime, we get 0 plus 4, which is positive. Right, and by the second derivative test, if f double prime is positive, we have a local min there, so that gives us a local min. Okay. And then I'm going to plug my next one in, -2, so that's going to be 4 times -2 plus 4, so this is going to be -8 plus 4, so that's actually negative, and getting a negative here gives me a max at -2. So as you can see, The second derivative test is actually a lot faster. A lot of good things about it. I don't have to choose values. I only have two possibilities. I have to plug in the critical points. Okay, and you know, it's easier to plug these in to the second derivative usually, because the second derivative ends up being, you know, a much simpler function. Okay. All right. Now moving along from here, if I wanted to say what the intervals were, of course I could say that f increases on negative infinity to negative 2 and from 0 to infinity. Okay, and I could say f decreases on negative 2 to 0. So, you know, that's helpful there. Okay. Now we found the critical points, we found whether they were maxes and mins. Now we're going to find inflection points. And I'm going to let you all guess on how we might actually find inflection points. Do you think we do it in a similar way as we find critical points? Right, we found that if f double prime of c is 0, then f has a possible inflection point. So that's what we're going to do. We're going to take f double prime, which I'm just going to write it again here, set it equal to 0, solve. Okay, so now that's pretty easy. You move the 4 over, divide by 4, x is going to be negative 1. Now this is what we call a possible inflection point. Okay, it may not be one. We have to be very, very diligent about this. A lot of people don't even realize this, but it is just because, I mean, it's the same thing. Just because the second derivative is 0 there does not automatically mean it's an inflection point. It means that it's possibly an inflection point. And we check this in the same way. I make my number line, I put negative 1 down, and I check f double prime on either side, and that's going to tell me about f. Okay. So, to the left of negative 1, say if I put in something like negative 2, so f double prime of negative 2, well, that will be negative 8 here plus 4, which is going to be negative 4, so the whole thing ends up being negative. And what does that say about f if f double prime is negative? What does that tell me? If you told me that that means f is decreasing, you were wrong. That actually means that f is concave down. Okay? Alright? So remember, f double prime gives concavity. It doesn't give increasing or decreasing. We already did that with f prime. And I'm saying that because a lot of people make this mistake. All right, and now to the right of negative 1, if I plug in 0, that's an easy one to do. 0, that will be positive 4. Okay, and as you see, I actually just plugged in what I already did for the second derivative test in here, which is often what ends up happening. So you often already have all that information. You don't have to do it again if you do the second derivative test. But that means that f is concave up on this interval. Okay, so we could say that f is concave up on negative 1 to infinity, and f is concave down on negative infinity to negative 1. And that means that x equal to negative 1 is an inflection point. You have to check this. We're going to look at an example next where you will have something that is actually potentially not an inflection point. All right, let's look at something like this: 1/4 x to the 4th minus x. This is an interesting example, okay? Because well, we'll get basically what I was talking about before. So we're going to do the whole shebang, everything we can. Let's take the derivative to start with. All right, so f prime of x is going to be x cubed minus 1. Now let's go ahead and take the second derivative, because, well, we're going to need that anyway. All right. So let's start by finding the critical points. Okay, so I will set x cubed minus 1 equal to 0 and solve. So I basically have that x cubed is equal to 1, which gives me that x is equal to 1. Okay. This is not plus or minus 1 since it's an odd root, or excuse me, an odd power. Okay, so here's my critical point. Now, I'm going to go ahead and use the second derivative test. Okay, so by the second derivative test, all I'm going to do is plug 1 into the second derivative, which ends up being positive. Now, what does positive on the second derivative test mean? It means we have a minimum there. Okay. And even though we didn't use the first derivative test, what we just found is we have a minimum at 1. So we could plot it wherever we want. Oh, you can't see that. No. So here's 1. If I have a minimum at 1, that means it looks like this. That means it's the only, since it's the only critical point, it's the only min. I could draw it up here, it doesn't really matter. But that means that f goes from decreasing to increasing. So you can actually get your intervals even though we use the second derivative test, right? So that means f is increases on 1 to infinity, and f decreases on negative infinity to 1. And see how much faster the second derivative test is compared to, say, the first derivative test? The only problem is it doesn't always work. But when it does, it is so much faster. Right? You don't have to do a whole lot. It's just like a one-line thing for each critical point, instead of like picking a bunch of values, having to choose values. Okay. So that's the critical points. Let's look at inflection points. So let's try to find the inflection points. Okay, so we're going to take the second derivative, which is 3x squared, and set it equal to 0. And let me go ahead and write it like that to show I'm setting it. And that definitely means that x is equal to 0. Right? 3x squared is equal to 0, x is equal to 0, and this is a possible inflection point. Okay, possible inflection point. We have to check to make sure. And here we do need to do our number line. That is always necessary for inflection points. Although in this case, we'll see in just a second that it's actually not always needed. But here's f double prime, here's f. If I plug in, I don't know, let's say f prime of -1, -1 squared will be positive, so that's positive. Right, so we have positive here. So what does that mean about f? If you said increasing, wrong. It is concave up. I can't tell you how many times I will hear that. And what do we have here? If I plug in something to the right of 0, say f of 1, we also get something that's positive, which will be concave up again. So f is going from concave up to concave up. That means that x equals 0 is not an inflection point. Okay. on an inflection point. So you won't always have an inflection point. In fact, this guy doesn't have an inflection point. Okay, if you're curious what this actually looks like in practice, what we have here is a possible inflection point, right? So what this graph basically does is at 0, it looks very linear for a while, okay? And then of course it has this local min at 1. But it looks linear for a while, but it doesn't actually change concavity. If it had started doing this, it would change concavity, but it didn't. It was like a fake out change in concavity. So that's what situations like this look like in practice. Okay? Okay, so I know now we have we're close to the hour mark, but I'm going to continue doing examples as long as it takes. Okay, if you feel like you've got it, that's your business. But I am going to start looking at some more examples for those of you who want to see more examples. Okay? But from this point on, it is just examples. So we're going to look at f of x equals x squared times e to the x. Okay? And we're going to do, everything we've talked about already. So I'm going to start by taking the derivative. Now you know we need to use the product rule here. So it'll be derivative of the first times the second plus the first left alone times the derivative of the second, which is thankfully just e to the x. And hey, this should look really familiar. You saw this on the worksheet. Right, and then we're going to take the second derivative. Okay, now the second derivative, here we'll have two product rules. So for this one, will be the derivative of the first, which is 2, times the second left alone, plus the first left alone times the derivative of the second. So that's the derivative of that first term. And then it will be the derivative of the second term, but we've already done that, right? We already did the derivative of x squared e to the x. That's just this. So I'm just going to copy that down. It's 2x e to the x plus x squared e to the x. Okay, and I'm going to simplify this. This will be 2 e to the x plus 4x e to the x plus x squared e to the x. Okay, so I'm just combining those middle terms there. All right, now let's find the critical points, which you have already done on a worksheet. We have 2x e to the x plus x squared e to the x is equal to 0, and I'm going to factor to start with, so I can factor out an x e to the x, and then I'm left with 2 plus x. So I'll go ahead and speed through this. You all already found that your critical points are 0 and negative 2. Okay, and now it's a question of, well, which test do I want to use? And my inkling is that I'm going to use the first derivative test, because the second derivative test would involve plugging 0 into this, which 0 wouldn't be bad, but then I have to plug negative 2 into this. Okay, so I'm going to go ahead and use the first derivative test. I feel like that's a little better. Okay, so I'll put negative 2, 0. And the nice thing about this is when I'm checking this, e to the x is always positive. Okay, so it's not going to affect what I find here for f prime. Okay. Cool. So that means I'm going to plug in something like negative 3. So that would make this piece negative. This piece is positive, and then this piece would be negative. So I have negative, positive, negative. So in this interval for negative 3, negative, positive, negative, that will be positive. So f is increasing. Okay. Now between negative 2 and 0, if I put in something like negative 1, I'm going to get negative here. I'm going to get positive here, since this is always positive. I just shouldn't erase that ever. And then -1, say, that's what I'm choosing, -1 plus that positive 2 will be positive. So I have negative, positive, positive. That will end up giving me a negative. So that means f is decreasing there. Okay. And then to the right of 0, if I put in a positive 1, let's say, well, 1 here, that'll be positive. This is always positive. 2 plus 1 will be positive, so it ends up being positive. All right, so I end up with a local max here at -2 and a local min here at 0. And I have my intervals of increasing and decreasing, right? F is increasing on -infinity to -2, union 0 to infinity. Let me shift that over so you can see it a little better. And then f is decreasing on -2 to 0. All right, so if you ask for intervals, we already have it. Okay, so now we're going to look at finding the inflection points. All right, so now we're going to start looking for the inflection points, the possible inflection points. So to do that, we're going to set the second derivative equal to 0. So I have it right here, the 2e to the x plus 4x e to the x plus x squared e to the x. And I'm going to start by factoring out that e to the x right here at the beginning. So I have e to the x times 2 plus 4x plus x squared equals 0. And this e to the x is not going to matter, right? If I have e to the x equals 0, that doesn't matter. So really all I have to concern myself with is this thing here. And unfortunately, this guy won't factor, but we can just use the quadratic formula, which would be negative b plus or minus the square root of b squared minus 4ac all over 2a. Now what we basically have on the inside here, that's 16 minus 8, so this ends up being negative 4 plus or minus the square root of 8 all over 2. And the square root of 8 I can actually rewrite as 2 times the square root of 2. And then the 2 will cancel with these guys. And so what I end up with is that x is equal to negative 2 plus or minus the square root of 2. So here are my possible IPs, my possible inflection points. Okay? So now we have to check, all right? And this, you might be running for your calculator right now, but I'll tell you, you don't really need it. You can actually do this whole problem without one. Because remember, we're not plugging these in. We're plugging things in around it. And here I have negative plus, so negative 2 plus the square root of 2. Square root of 2 is way less than 2. Square roots are always less than whatever you're taking the square root of. So I know this is some negative number. That means 0 lives over here. So for this region, right, I could look at f double prime of 0, which is actually not a very tough thing to look at, right? So you plug in 0, right? When you're checking f double prime, let me write it again over here. This thing is always going to be positive, okay? Always. So really we're just looking at this. So when I plug in 0, I get 2 plus 0 plus 0, so this thing ends up being positive. So I get that it's concave up. Now yeah, I'm going the other way here. Doesn't really matter, okay? Now, between negative 2 minus square root of 2 and negative 2 plus square root of 2, negative 2 sits, right? I'm adding and subtracting the exact same thing from negative 2, so right in the middle, negative 2 should live there. So now we're going to look at f double prime of negative 2. Now I might write it over here, because this thing will always be positive, but then we'll get 2, okay, minus 8 plus 2 squared, or negative 2 squared, which is 4. Alright, so I have 2 plus 4, that'll be 6 minus 8. So this thing is actually negative. So I have a positive times a negative, so the thing will be negative. Okay, so that means that F is concave down in this region. And then finally over here, this one's a little tougher, but I have negative 2 minus the square root of 2. Now square root of 2 is less than square root of 4. That's my next, known square root. And so square root of 4 would be 2. So I know that negative 4 lives over here. But there are, other things you could choose. You could also choose negative 10 if you wanted to be like super, if you wanted to overkill, do super overkill, right? So now I'm going to plug in negative 4. So I have 2, that doesn't change, minus 4 times 4, so that's minus 16, okay, then plus negative 4 all squared, which will be plus 16, so those cancel out and I get positive. I have a positive times a positive, so this guy is going to be positive, meaning that F is concave up in this region. Okay, so F is concave up on negative infinity to negative 2 minus the square root of 2 union negative 2 plus the square root of 2 to infinity. And then F is concave down on negative 2 minus the square root of 2 all the way to negative 2 plus the square root of 2. Meaning that x equals negative 2 or basically that x equals negative 2 plus or minus the square root of 2 are both inflection points. Alright, and this is essentially what this graph looks like for those of you who are interested. Since it's x squared times e to the x, the e to the x does take over for the most part, but x squared does start to try and because as e to the x goes to 0, it goes to 0 faster than x squared will be increasing, but here around negative 2 you see it actually does kind of start to take over, and they both go to infinity together over here. But here are your inflection points where you had the negative 2 minus the square root of 2 and negative 2 plus the square root of 2. You could say that this distance here is square root of 2. Okay, so if you were curious about what this looked like, and eventually we will take a look at how to graph these by hand and see what's going on there. But for now, we'll just move on. Okay, so there are many, many more examples I would love to look at, but let's just do one more. Again, there are countless ways you can iterate on this and make things different, but we're going to look at f of x equals x times the natural log of x. Right? So we always start by taking the derivative, and this will be a product rule. So it'll be derivative of the first, which is 1, times the second, so it's just natural log of x, plus the first left alone times the derivative of the second. So we actually get that this is just ln x plus 1. Alright, not too bad. And then we are going to take a look at the second derivative, which is going to be just simply 1 over x. So now we're going to find the critical points by taking the first derivative, ln x plus 1, and setting it equal to 0 and solving. Okay, so let's go ahead and do that. Ln x is equal to negative 1, and from here all we've got to do is basically raise both sides to the e. Right, if ln of x is equal to 1, that means e to the negative 1 is equal to x. So you can either raise both sides to the e, or you can just use the properties of logs. In other words, x is equal to 1 over e. So this is our critical point. Okay. And I'm going to analyze this critical point using the second derivative test. All right, it's going to be super easy because I don't have to worry about picking values to the left and right of 1 over e and all that. And you might not think that that's a big deal, but remember, natural log of x, the domain of this thing, domain is 0 to infinity, right? So you can't plug in 0, which might be something you would think you could do here when you check. Right? That's something you also have to be super careful about. Basically what I'm saying, if you did 1 over e, you could not choose 0 on this side, right? You'd have to pick something between there. So actually, the second derivative test is much easier. So second derivative, to remind you, is this. So f double prime, and I'm just going to plug 1 over e into that. So this is going to be 1 over e, which is e, and that's positive. So we have a positive, which means we have a min at 1 over e. Okay. All right. Right now we're going to check for inflection points, and actually we can find here that very quickly f double prime of x is 1 over x, and well, if we set that equal to 0, there's actually no solution. A fraction's only 0 if the top is equal to 0 and the bottom isn't. Now you might think that f double prime is undefined, right, at x equals 0. So you might think that that is helpful, but it's really not, because so is the original function, right? But so is f. So it actually doesn't, it's not something we check for an inflection point. It can't be an inflection point because f doesn't even exist there. And that doesn't necessarily mean f can't change inflection at a place where it doesn't exist. For example, if you have an asymptote, you can change from concave up to concave down, right? So you can change inflection at a point where a function does not exist. But in this case, f doesn't exist to the left of 0. I mean, it's acting something like this. So there's nothing over here. So there's nothing to change from on that side, essentially. Okay, so we don't actually have to worry about 0. So basically, f has no inflection points, right? Which is definitely possible. I mean, if you, all this just means is that if we're looking, I mean, we are looking from 0 to infinity, that's the domain, and 1 over x is always going to be positive on that domain. So we basically have that, right, so 1 over x is always, and not equal, ever equal, it's always positive on 0 to infinity, so f is always concave up. So the way I drew it here is actually wrong. It probably looks a little more like this. It's all said and done. Okay, so that's the last example I wanted to look at for this. Again, there's so many different ways we can look at this, but we'll have more examples to look at in section 4.3. That's where we put all this stuff together and actually start graphing these things by hand. So if there's more examples you would like to see, you will definitely see some more. Okay, so talk then. Cheers.